All right, there it is. All right, so we're gonna go over topological sort and strongly connected components today. Here's a link to the slides so you can follow along. I think people have got it by now, so I'll move on. You can stop me if you. Oh, it seems like people can't access the slides. So we'll figure that out. I think I fixed it. Can people try reloading the link? All right, I think it works now. So let's get started. So topological sort is an algorithm that's on a DAG. So what a DAG is it's a directed acyclic graph. And basically this means like, so every edge is from a vertex to another vertex, right? It's not both ways. There's a specific order to the edge. And there's also no cycle. So for every path, there's no path that goes from the end to the start. You can't go back in the cycle. And one thing we can do with this is to model dependencies. Like if you're doing a bunch of tasks and say one task needs to be completed after another task, I don't know, like emptying the dishwasher has to be done after doing the dishes, something like that. So then you would have like a node for each task, and then the dependency is one of the edge. So it points to the task that must be completed afterwards. So if there's no cycles and if there's no cycles and every edge is directed, it's considered a DAG. And one question that we have is that can we order nodes such that all the edges follow the order? So let's say, so in like a task analogy, is there an order I can do the task such that all my edges are satisfied? That like every node that I said has to be completed after a different node, like we follow that restriction. So does anyone have any ideas that of whether this is even possible or how we might do it? You can either unmute yourself or type in the chat. Or just any kind of intuition or properties you see that might be helpful to us about DAGs. All right, maybe first node in the order has no dependencies. That's true. Because the first task you have to do obviously can't have any like restriction that it must come after a certain other task. That's true. Does anyone think this might not be possible, or like what do we need to be sure that this is possible and that to get such an order? Or maybe in the chat you can just type in whether you think it's possible or not. How about that? All right, I'll just move on. It is possible on all DAGs. And I'll prove this with a sort of constructive proof. So we'll go through the algorithm and we'll prove the algorithm always works. Yeah, we'll prove that the algorithm always works on a DAG. And the way the algorithm is based on DFS. So you'll have to know DFS, understand this part, but I'll try to go through all the steps. So the way the algorithm works is we first start off with an empty list, and this list is going to be the order at the end. And what we do is we perform a DFS on the graph. We start on any node. It doesn't have to be the node that has no dependency. It could be any node. And every time you backtrack from a node, we add to a list. So if you remember in DFS, you start a node, then you explore, and you call it the function on all its children that haven't been visited. And then we backtrack from that node. So then we can go back to these ancestors. Okay, and then so every node in a DAG will be visited because that's how DFS works, right? So we visit every node, and once we do that, we have a list of all the nodes, and at the end we reverse that list, and this is our topological sort. And one property here is that the nodes are in reverse finishing time order. And what that means is when you do DFS, what you do is you visit every node, right? And then you visit its children, and then its children, and you keep going, and then you backtrack. So the step that you backtrack is the finishing step. So every node has a visited step and a finishing step, right? So the first time you see that node, and then the last time you see that node. So the property of the topological sort of this algorithm is that when we do a DFS, we have the nodes in reverse finishing time order. Let's see. All right, so I guess I hope if anyone has any questions about the algorithm, you can type in the chat or just unmute yourself. Otherwise, we'll move on. I'll give you guys a few seconds to ask any questions. All right, I'm going to assume there's no more questions. And we'll go to the proof why this works on any directed acyclic graph.
Wait, all right, I have a question.
Sure.
So maybe I missed this, but what happens if there's a node that DFS doesn't visit because there's no path to it from where we started?
Well, I guess like in the DFS algorithm, it depends on your DFS algorithm, but in this specific DFS algorithm, it's like you go through all the nodes, which is like let's say there's a node that you haven't explored yet, then you would just do DFS from that node.
Okay, so it's like DFS inside of like a for loop over all the nodes, but obviously you wouldn't start it if you already visited it. That's sort of
Yeah, so like you would have like I guess you would have like the helper function, and which does DFS on like a connected part of a graph. And then the main function would actually go through all the vertices to make sure that we have visited every vertex and do uncall DFS on the vertices that we haven't visited. Yeah.
Okay. Thank you.
Yeah. So I guess we'll go through we'll see how the algorithm works in a little bit, but so important thing is that we do visit every vertex, and the property of reverse finishing time still applies. Yeah. Does anyone have any other questions? Okay. Yeah, so we'll go through a proof, and we'll assume for contradiction that like in the order, so let's say this is the order, C, B, E, A, D, F, G. This is the graph that it came with, but let's say there was some I guess this graph isn't particular to the proof, but let's say there was some edge from F to E where F comes after E in the order that we returned. So some properties of the graph is that we know there's no cycle since it's a DAG, right? So it's acyclic. So there's no path from E to F. Since if there was a path from E to F, then we would have a cycle, right? And E must finish after F because of the reverse finishing time property. And then let me move on. So there's two cases. When we do the DFS algorithm, either we visit E first or we visit F first. So if E was visited first, then we know that F is not a descendant of E, right? Because there's no path from E to F, which we just said. And so therefore, E must finish before F is visited. But by the ordering, we know E finished after F, so this case can't be true. So in the other case, if F was visited, then the algorithm would go from F to E, right? Because there's an edge from F to E. So when it visits F, it would go from F to E, explore E descendants, backtrack from E, and then go back and then go to F, right? But that would have to mean that E finished before F. So this is also not possible. So in both cases, we found the contradiction, and therefore there can't be an edge from F to E if F comes after E in the order. And this proof shows that topological sort works, gives us such an ordering, and it works on every possible DAG, since we didn't make any assumptions about the graph other than it's directed and acyclic. So yeah, so I guess you can ask any questions now in the chat or unmute yourself. And let me launch a poll. Okay, it seems like most of you thought the explanation was clear. If you do want me to explain again, maybe you can tell me which part you want me to explain again. Or any part you're confused on, anything. It's fine, I can go back and talk more about it. All right, I guess we can move on. And yeah, so we can extract some main ideas from this topological sort. And like the key idea here is that we know that all the children of a node must appear afterwards in the order, right? So this is like a recursive kind of restriction, right? Because you have a node and all its children must appear after that, and all of those children's children must appear after that, and so on, right? So when you first see something like this, right, you think all like this recursive restrictions, right? How can I solve it? And DFS is one of our recursive tools that we can use to solve problems like this, right? Where we have like restrictions based on like children's like that. And I guess like when you first see something like this, it's hard to know how to solve the problem. But when you think about like what type of restrictions these are and what type of tools I have, and the solution becomes more obvious. And so now we'll go into how the algorithm works. This algorithm actually extends the topological sort algorithm. And what it does is it detects if there's a cycle in the graph, right? So now we're not just taking any directed acyclic graph, we're taking any directed graph. And the algorithm outputs if it finds a cycle, or if it doesn't have a cycle, it outputs a topological sort. So the way we determine if a directed graph has a cycle is using DFS or BFS. You could also use BFS, but the idea is that since we're already doing a DFS, then we can determine if it has a cycle and therefore combine the algorithms and just work on any directed graph. And the algorithm has like the main part of the algorithm is at the top, where we have the while exist nodes. So we go through all the nodes and find any node that doesn't have that hasn't been visited yet, and then we visit that. So that's our DFS right there. And we continue. Then we recursively call visit again, and finally we get L, which is the topological sort. And I think in this algorithm it doesn't reverse it. It doesn't really matter. depending on the problem, you may want to reverse it, you may not want to reverse it. Any questions? Maybe I'll talk about why, how we're determining if you have a cycle. So actually, maybe someone wants to tell us like how to determine if a directed graph has a cycle. You can type in the chat, or any ideas of how you can determine if a directed graph has a cycle.
If you reach a vertex that you've already marked in your current DFS, but not completed searching the children of, then you're back at an ancestor vertex.
Yeah, that's pretty much it. So in a directed acyclic graph, when you do the DFS, we know that whenever, if we ever visit the same node again, it must have been from a vertex that's not a descendant. And in a cycle, what you have is that when you start on one of the vertex in the cycle, as you DFS, eventually you'll come back to the same vertex. So yeah, try top sort it, but it depends on your algorithm. If your algorithm doesn't account for the fact that the graph may have cycles, then the top sort will work, but it won't be a valid topological sort. So yeah. And this is basically what it does. What he said is that as we DFS it, we have two marks. We have a temporary mark and a permanent mark. Temporary mark means it's still being visited, right? So we haven't finished visiting that vertex. So if you ever see the edge, see the node again, then we know we found a cycle. Okay, and this is I just coded this up in Python, and this is more similar to the algorithm beforehand. It doesn't detect any cycles. So if you did give this a cycle graph, it would just happily return a topological order that's not valid. But you can see how this works. So we have a main function called topological sort, and it calls DFS on all the vertices as long as they're not visited. And finally, we reverse it at the end. And this graph is actually the same graph that was in the description. It was in the description before, so I tested it and it all works. Move on. So now our second topic here is strongly connected components. So what does it mean to be strongly connected? And what that means is that every pair of vertices has a path, right? So you can see like in the example graph, right? So there's two strongly connected components. There's three strongly connected components, and in the first one, like we have 0, 1, and 2. So you pick any two of those. There's a path from 0 to 1, 1 to 0, 0 to 2, 2 to 1, right? And so strongly connected components. This problem has to do with breaking up the graph into components such that all of them are strongly connected, but also that if we can create a strongly connected component graph from this, right? So if you look on the right, we have that graph, and what that graph is it represents, each node represents a strongly connected component, and each edge represents a path from a node in one of the each edge represents an edge in the original graph from one of the nodes in one of the strongly connected component to the other strongly connected component, and this graph must be a DAG. If you think about it, right, well, it can't be just it can't be a regular directed graph, right? Because if there is a cycle in this new graph, well, it means that there's a strongly connected component that we've broken up, right? So let's say like if there was an edge from the the middle vertex, right? 3 to 0, 1, and 2, right? If there was an edge from 3 to 2, well, that means that there's a that means there's a path from 3 to 0, 1, and 2, right? So that means that 3 should actually be part of the strongly connected component that 0, 1, and 2 are in, right? So now what we're doing here is that we're saying all of these edges, all of these nodes can reach each other, and they can reach all the nodes that come after it in the graph of SCCs, right? So 0, 1, and 2 can reach 0, 1, 2, 3, 4. 3 can reach 4, and 4 can't reach anyone. So that's what this graph represents. Does everyone understand what the problem is and like what we're looking for here? Yeah, all right, so I'll move on. So there's a main algorithm here called Kosa-Raju's algorithm, and it's a little unintuitive in my opinion, but it's not too hard to implement. And the first part of it is actually doing a topological sort algorithm, which not the one that I implemented in Python, the one that doesn't check for cycles. And even though it is a directed graph, it will still return an order, right? Because we're not checking for cycles. But that order is not a topological order, but it is going to be used in this algorithm. And so we find that order, we call it S, right? Then we reverse the graph, and then for all the vertices, and we visit all the vertices in the order that S was, right? Whatever the topological sort returned, we visit the vertices in that order, and we use that to create our strongly connected components, right? So every vertex in S, we do a DFS on it, and the vertices reachable from that vertex in the reversed, in like a transposed graph, right? So it's important that we transpose all the edges between the topological sort and the rest of the algorithm. Then we do DFS from all of those, and all the vertices reached are part of that strongly connected component. Hopefully this makes sense. If anyone has any questions, please ask.
Hey, sorry, would you mind going over that again?
Yeah, sure. So the way the algorithm works is that we first do the topological sort algorithm, right? Which is where we do a DFS on over all the nodes, and we remember the nodes in finishing time. So instead, and here we don't reverse it. So we have all the nodes in the finishing time. So that's what S is. It represents the nodes that are sorted in finishing time. And we go through, well, first we reverse the graph. We reverse all the edges for every edge from V to U, we reverse it, so it's from U to V. And then we go through the vertices in the graph in the order of S. So in the order of the finishing time. So the vertex that finished the first is the first vertex we're going to DFS on, and we're going to find all the vertices that's reachable from it in the transposed graph. And that's the strongly connected component. And we can keep doing this. Yeah, is there any particular part that that's confusing? I know it's a little unintuitive as to why we're doing all of this, but the best way I can explain it is that if you transpose all the edges, right, that from the new graph still should have the same strongly connected components, right? And also, if we take the graph, the graph of the original graph, and we do DFS on it, the vertex that finished last must be in the last node of the strongly connected component graph, right? the strongly connected component graph, if you recall, was the graph where we took all the strongly connected components, made them each a node, and made edges between the ones that can be reached from the other. So if you look at that graph, it tells you that the vertex that finishes the first must be at the end of the order. So if so that's like kind of the intuition that we have, is that what we're doing is that we're going from the maybe if I'll go back a little bit. What we're doing here is like, okay, so when we do the topological sort here algorithm here, we'll get 4 has to be the vertex that finishes last. Sorry, finishes first. Right. I mean, you can take a moment to see that yourself. But if you do DFS from any vertex, you're gonna backtrack from 4 first, because they all have a path to 4. And then what we do is that we're doing DFS on 4 and finding all the vertices that are reachable from it in the transpose graph.
Wait, so what if you started from vertex 0 and then you went to 2 and then 1, and then 1 finished first, and you go all the way back up to 0 and then you do 3 and 4?
Yeah. So let me think about that.
You're saying like there exists a DFS tree for which like 4 finishes first?
No, I think you should be able to DFS on starting from any node. Let me pull up the algorithm again. 1 second. Okay, so I think, yeah, so if you start from 0, then you're gonna find sorry, just 1 second, let me just think about this. If anyone else wants to jump in, they know how this works, go ahead. But I think you should be able to start from any node, and the topological sort that it returns should be sorry, 1 second. Okay, so what we do here is that we, in a topological sort algorithm, what we do is we find the vertex and we order them in like finishing time. And I think it should, okay, yeah, I think it's, okay, yeah, so it's definitely possible that 1 is the first one, but I think it should still work, because what we do is you remember we have to transpose the graph. So so now the new edges, we have like an edge from 0 to 1, from 1 to 2, and 2 to 0, and from 3 to 0. So if we do DFS from 1, we're not going to be able to reach 3 or 4. So we're going to end up with 0, 1, and 2 as a vertices that are reachable from 1 in the transpose graph. So we still get the correct strongly connected component. If that makes sense. So the topological ordering is useful because it's basically just the vertices in the order of finishing time. So that has its own properties. Yeah.
So, like, suppose you think of the graph as like a DAG on these strongly connected components. Would it be
Sure.
correct to say that this like kind of like fake topological sort is still a topological ordering on the strongly connected components? Like if a whole strongly connected component like comes before another whole strongly connected component, then like seems like every vertex in that one should, in the first strongly connected component, should come before every vertex in the second one. And then I think like then when you reverse the edges, yeah, I think that it like works.
Yeah, I think that's definitely like one of the properties that when we have like the finishing times of the vertices, we have like some kind of ordering in like that corresponds to topological sort in the strongly connected component graph, because like any vertex that let's say you have like two strongly connected components where like one points to the other, then like we know that like the first, like I mean, all that matters is which one had a node that finished first, and we know that if let's say there's two strongly connected components U and V, then a node that is in V, one of them has to at least finish before all the nodes in U, because every node in U has a path to V, right? So when we are doing DFS, we're going to visit a node in U, and then all of them have a children, which is a node in V. Does that make sense? So that's how we get that. Yeah, that's how that property is what allows the algorithm to work.
Okay.
And that,
Okay. I see what you're saying. I think what I said was too strong and it's like not correct, but yeah, that sounds good. That sounds good.
yeah. So it's kind of like a unintuitive algorithm where you really need to think about why it works, but the idea of using the graph of the strongly connected components is pretty helpful to understanding why this might work. And like another property that I said was that if you transpose a graph, which is you reverse all the edges, then it still has to have the same strongly connected components, and we can see that in this one. But like it's also a pretty simple proof. You can do that like yourself. Yeah, so if anyone else has any questions, please feel free to jump in, ask a question in chat. I'll launch the poll. Um, Yeah, I know it's a little a strange topic, and the algorithm is not something you could come up with pretty quickly. So, but it seems like most people understand this. All right. So then I think if you guys, I mean, if you want me to explain some part of it again, you can type in the chat which part you want me to explain again. Go through. If you want me to go through an example, you can say that too. Anything I can go over. Just feel free to say what you want me to do. And if you want to see some example code, you can simply search up Kosa-Raju's algorithm. I think there's implementations on this website called CP Algorithms. So there's plenty of implementations, but I think CP Algorithms was recommended by someone on the ICPC team. All right. So this is the attendance code, and I think we're gonna do some Codeforces problems.